Hi, friends of the sun. Welcome to our reading group where every Monday, every week, we discuss some paper with the authors of that paper. Yeah, and we do that via Zoom, so you can join yourself. Just find the website, click on the link, and nothing else. And if you want to join our mailing list or Slack or stuff like that, all the information is down in the description. So let's get to some knowledge graph learning paper with Mikhail Galkin. Let's go.
Yeah, so hello everyone. Good morning. Uh, Good evening if you're in Europe. My name is Michael. I am a research scientist at Intel. Previously, I was a postdoc at Mila in the group of Geopark, so we continue to collab. And I work on graph machine learning, geometric learning, and part of my work recently we released a the first foundation model for knowledge graph reasoning, about which I'll be talking today. So yeah, let's start. So this is a collaborative project with Mila students and with some Intel folks. And this has recently been accepted to ICLR 2024. So we have one more additional uh, celebration. uh, yeah. Uh, so January is that we have noticed indeed. January is the month of graphs at the a log reading group. So all four presentations except for one for Monday first. It was uh, we're surprisingly on more on graphs. And we'll continue the trend today, but don't be afraid. Starting from February already, going back to the fusion models, uh, which might be my favorite topics as well. Yeah. So a few words about knowledge graphs of what we are working with here. So those are multi-relational graphs. So the graphs with edge types. Usually they are written as triples. You have subject, predicate, object. And those are very multi-domain graphs. They're general encyclopedia-like graphs, like Wikidata and Freebase. They usually have something to do with Wikipedia. And those graphs power a lot of search engines, like Google Knowledge Graph, Microsoft Knowledge Graph. They pretty much everywhere if you search for something. So all this structured information usually is taken from some unified knowledge resource. And right now it's all rage for some retrieval augmented generation LLMs. There is a bunch of scientific graphs, for instance, UniProt, on which people train protein language models like ESM. UniProt is, in fact, a triple-based knowledge graph. Well, there is one distribution of it, so can also encode some scientific information. And there are many smaller custom domain graphs, like some urban graphs that I discovered recently, and a bunch of closed source enterprise graphs. And we want to have some representation learning mechanism for them as well. Their basic representation is something that can also be called RDF, Resource Description Framework. So that's basically how we encode those triples in some structured format that might have some semantics, but it's the last time in this talk I will say something about semantics because nobody's interested into that. But I'll be using those images for references further. So those are vanilla triple-based graphs. And a few more formalities that those graphs are directed graphs. We have explicit relation types. Important thing that input node features are usually not given because there is so much a variety of them is that you cannot train any transferable model if one graph has, I know, bird features, the other one has numerical features. So we just assume that they are not given. And there are several setups called the transductive and inductive. Transductive is when you run inference on the same graph you have trained. If you have one 1 billion node graph. Or inductive, it means that when your graph is completely different at test time. And there are several versions of that inductiveness, so briefly cover as well. And our basic task, so knowledge graph reasoning, or knowledge here is knowledge graph completion. That it's the basic building block of the knowledge graph reasoning. So there, we have a query, and we have which consists of head and relation, and we have to build a distribution over all nodes in the graph. So we have here, as an example, we have starting node, we have some relation type, say a green one, and we want to probable nodes, whether they are true tails on that. A few words of difference from the last week's presentation of Surreal. It was talking about link prediction, and there are small differences between KG completion and link prediction. So in KG completion, usually we work with queries in the form starting node, some relation type, and we build a distribution over all nodes. While in link prediction, consider, for instance, in Surreal and homogeneous graphs, usually we are interested in we were given two nodes and we have to build a function of two nodes. And then we just return a binary or a binary tag or a multi label tag saying that whether there is a link between those two. But we know source and the tail beforehand. In the KG completion case, we do not know that. So the way to transform, for instance, the link prediction to KG completion is that we have to probe all possible pairs of nodes, and that makes things much longer and computationally expensive. Yeah, so we are focusing here on the KG completion task.
Hi, is
Yeah,
is
go ahead.
there any way to identify a transductive versus a inductive graph here?
Yeah, that's exactly my slide. This is slide is
Okay.
about. So
Okay.
in transductive setup, the same graph that we had with all its entities and relation types, it's the same at inference. And inductive graph, it means that we have something different. Something different might be a setup when we have a new node, for instance, attaching to the main graph at inference time. So for instance, you update your graph with a new bunch of nodes. Or you have a completely different disjoint graph at inference. So you want to build a generalistic model that you can train on one graph and run inference on everything else. That's actually the topic of today's talk. And so far, that hasn't been done in the community, surprisingly. And yeah, for inductive reasoning, the task is it's principally the same. So we still have the same queries, but now the domain on which you are running those functions is different. So graph might be different. We might have new nodes or new relation types. That's so far the hardest of them all. So if you have some, well, I'll be talking about the main problems there. Yeah, so some brief history of those approaches is actually pretty old. If you look back, everything started even before the rise of deep learning. So first models for embedding those graphs appeared around 2011. So this is Rascal by Mikhail and Mikhail. Then another famous model, translation embedding, from 2013. And those models were shallow embedding models. It means that you have your graph with 10,000, 1 million nodes, and you learn pretty much a linear model, sort of a word-to-vec-like model when you associate every node with its own learnable vector. And the same for each relation type, you would associate a relation with a vector. So in the end, you have a huge vocabulary of entities and relations. If you have 1 million of nodes, you'll have an embedding table of 1 million rows. So it is old. It is not efficient at all. It is not transferable. And surprisingly, this is still very popular. So since then, so those times, we have hundreds and hundreds of those shallow embedding models that pretty much stale in the performance. They only target one small setup, which is called transductive setup over triple graphs. And the performance there is stale. So for about already 6 years, nothing happens in the area of shallow transductive models. And if we look at the papers with code, for instance, then all of those benchmarks and all the major benchmarks, the performance is stale somewhere around this is the same point for now. And they needed some huge kick to revive back the interest into the topic. And luckily, we have that, which are graph nets. Finally, we can combat linear graph embedding models with something less linear. And that was the subject brought by geometric deep learning. And now we can apply a bunch of different GNS. And finally, the area has become more interesting and more progress appeared around that time. And one of the important breakthroughs here is the NeurIPS 21 work called Neural Bellman-Ford. nets, and this actually has quite some profound impact, not only in KG reasoning, but also in algorithmic alignment and general link prediction and so on. So this is a general framework for doing link prediction homogeneous or multi-relational graphs. The idea there is using a labeling trick, and that's important. So labeling tricks, again, were described last week with the surreal work, and LBF nets also use some version of its of the labeling trick. So we still have the main task as a link predictor. We have a starting node would have, and we have a query relation, and the main assumption that, well, we actually don't need the entity embeddings in that sense. We can use a vector of a query of relation type as the starting initialization for the target node. And then we will initialize everything else with zeros. So this is a labeling trick with an indicator function. So in this labeling scheme, we initialize one single node with the non-zero vector. All other nodes are zeros. And then we run message passing, standard message passing like MP and nlag. And at the end, there are some theoretical properties. Saying that at the end, the final node states capture pairwise relationships. So every node state of the node of any node here captures how this node interacts with the starting head node. In fact, it encodes Bellman for the iteration. So that was the main point of NBFNet paper. And so it can probably discover shortest paths. Under certain assumptions, can approximate other centrality metrics like PageRank and so on. So it is a nice pairwise encoder, which at the end of the iteration give you a distribution of tails given head and relation. So this is a really profoundly impactful GNN model that crushed all the benchmarks and dramatically improved all the numbers compared to those shallow linear embedding models. And it's inductive by design, inductive to the entities. So we still learn relation types, but we do not need to learn entity embeddings anymore. So we can drop all those 1 million rows embedding tables and can just learn the number of relations. Usually the number of relation types in those graphs is small, like not more than 1,000. So we can afford that. And perhaps the only formula in this whole presentation is just encoding how it works formally, that we have certain indicator functions. So we put some vector on the head node, and then this is a standard message passing interface and nothing. And a few other labeling tricks that were mentioned last week as well, and pretty popular in the community. For instance, this is a distance encoding, perhaps the most classic of them all. So you extract a subgraph around target nodes UNV. So this is a setup of homogeneous node prediction. Then you'll just label nodes in the neighborhood. For instance, this node in the middle, they are one hop away from both source and target node. So you just put a label 1, 1 on them, and so on. So the problem there is neighborhood sampling and enumeration of those neighborhoods. That's why it has exponential complexity. And many methods, like last week's surreal, try to approximate and not find a way not to sample those neighborhoods, and they are actually pretty effective in that. For multi-relational graphs, that has been adapted. That was a ICML 2020 work called Grail. So it uses the same labeling approach, now enriched with edge types. And then this has been pretty much the first inductive KG completion method suitable for multi-relational graphs. And its problem is scalability. So it pretty much doesn't scale to anything large, and we want to solve that problem as well. Cool. So after appearance of geometric deep learning GNNs and neural Bellman for nets, we are at the stage that we can train inductive models that transfer to new entities, but we still cannot transfer to graphs with new relations. So it means that if you have your own one big graph, say UniProt, you can only train a model on UniProt. You cannot transfer the model to any other multi-relational graph. So every time with a new graph, you have to retrain it again and again. And this is just not efficient, wasteful, and there are algorithms already that can do better. So the main problem of the work we have done is we try to find ways how to generalize to both new nodes and relation types at inference. Ideally, we want to have some sort of foundation model, for which you have only one foundation model for all possible kind of graphs. A useful example for that is there are two big graphs called Freebase and Wikidata. Freebase is actually some graph behind the Google Knowledge Graph. Freebase is surprisingly used in the community, and for the reasons we do not completely understand, because it's sort of a necromancy. The graph is dead since 2007, so for more than 15 years, and people still use it for benchmarking. So this is a good example of necromancy that exists in the machine learning community. It's an example of a very big graph, about 90 million nodes, 1,500 relations. It's an encyclopedia-like graph. And there is Wikidata, which is now the most used open source, open graph, which powers many applications. It also has about 100 million nodes and 6,000 relations. The point is that if you want to embed those graphs in shallow methods, you would have to build those huge, enormous embedding tables of 100 million rows or 86 million rows. And you would waste that compute tailoring your embedding model for one particular graph. And we don't want that. We want to have one. Practically, we want to have a pre-train and fine-tune paradigm, something that you can train on one or several graphs and then just transfer it to everything else possible in the zero-shot way, or if you want to, just in a fine-tuning fashion as well. The main question here is, what is transferable invariance? So if you have those different graphs that you can, well, by the fact that you learn those embedding tables, you already know, you can identify some vectors. You have your anchors, which are entities and relations. But if we do not want to learn those embedding tables, so what is the transferable invariance? What can we learn? If those are not entities or relation types, that we can reuse in graphs with new entities and new relation types. And so far, this has been surprisingly less explored topic. And for that, we need to learn, go deeply a bit into those labeling trick works, which also called conditional in prediction. So most models, most inductive models, they still learn relation embeddings. They use some labeling tricks. And they only transfer to graphs with the same relation type. This is called relative entity representation. So conceptually, if we think about those relative entity representations, see, we have two graphs here about Michael Jackson and about Beatles. They share the same set of relation types. So if we start message passing, initializing Michael Jackson node and everything else at 0, so we sort of put Michael Jackson node at the center of our coordinates. And after doing message passing, all other node has certain relation to that, so they are connected, and we can put them on some sort of a plane here. And then every representation of that node will have certain relation to the center of the coordinates. And the fact that we have the same set of relation types, if we have a different set of entities, so we can still have a similar geometry here. That allows us to transfer and to transfer to new entities, and this is done in those NBFNets, Neural Performance, and a few other NBFNet like GNN. So extending it to new relation types, as we come out with a humble, generous name of Ultra called Unified Learnable and Transferable Representation, which stands for Unified Learnable and Transferable Representations. And here we introduce it to relative relation representation. This slide is a bit huge, so I'll break it up step by step. The idea is, if we don't want to build a graph, if we want to learn relation types, let's try to learn something relative, something that is shared between relations, but not the relations themselves. So some relative interactions. And the simplest case of that is just a graph of relations. So we have a function of a graph that builds us how relations interact with each other. So for instance, if we have just this small subgraph that Michael Jackson collabed with Quincy Jones and authored Thriller, so we know that authored and collab as relations, they are incident. And it means that they share the same head node. So it means that in this graph of relation, we can build an edge that from author to collab as relations. So now they are nodes in the relational graph. There is a head-to-head relation, meaning that somewhere in the graph, there is one incident node on which those two relations share the same thing. Similarly, we can derive, for instance, tail to head. So if we know that Michael Jackson author Thriller and Thriller is of genre disc, debatable question, but we keep it like this one. It's a genre disc. So again, authored has a tail, a sum node. We're not interested in which node, we're just interested this node exists. A sum node, which is a head of another relation. So that's why we put the tail to head edge type between those in the graph of relation. And if we know that Thriller and Quincy Jones both worked in the genre of disco, then we can actually have a self-looping relation with type tail to tail. It means that somewhere in the graph, there is one node and where this edge of this relation type meet at the same tail node. And overall, we have those four meta relations, so like head to head, tail to tail, tail to head, and then head to tail. Some of them are inverses of each other, but that's actually good for message passing. And overall, we have a meta graph, which is actually pretty small, given that even in largest graphs, we don't have often more than 1,000 relation types. We can actually, yeah, it's a small overhead in the end. So we're building a graph of relations, and the big observation is that relations between relations remain the same. So whatever your graph is, being it encyclopedia graph, being it uniprot, being some scientific graph, being it some domain-specific graph, those relative relations actually transfer. So since those are independent from relation identity, whatever graph you take, if it's a directed graph, there will always be those meta relations like head to head, tail to tail, and so on. So this actually is transferable invariance. One of transferable invariances. This is so far perhaps the easiest one to explain and to explore. Yeah, so four of them, and that's actually the main principal idea. So let's not learn any entity relation bindings. Let's learn some meta relations from this meta graph, relational graph, and use those for MVFnet-like reasoning. And this is called relative relation representations. So if we have now at inference time, we have a graph with completely different relation types, we still have a similar graph of relations. So here is a very different graph of this. Here is Michael Jackson with the Thriller and disco. This graph is about Donald Milton Turing Award, and they have pretty much nothing in common, well, except topological pattern. That's a different thing. And actually, the graph of relations for them is the same. So that is the transferable invariance that we can reuse and learn in our graph models. Yeah. So having that. Oh yeah, there is a question. Go ahead.
Yes. Hello, Michael. I have two small questions. So I just want to have some sense about what type of graphs will probably fail in this regime, because it seems that there is some underlying assumption that those edge types will be present in different subgraphs inside the larger graph. And like if we would, for example, be working with label property graphs with a small number of edge types and they would not be very large, then probably this would not generalize. That's just like for your intuition, how many different edge types should we have for expressivity here and the size of graph? And the second question, have you tried, so if I understand correctly, here you just consider like a second order relation between edge types if a single node is a point of concision, right? Have you considered a weighting scheme where you just weight those secondary edges in the edge graph by the number of nodes that sort of okay, yeah.
So with the first question, you need more than two relation types. It works with everything more than two. And technically, you can even have homogeneous graphs represented as multi-relation graphs with just one single relation type, but then of course your graph of relations will be kind of useless. But for that reasons, you can probably come up with some PageRank based positional structural encodings from the graph and use those as transferable features. So this is they will be transferable. And besides, I would mention here the GPSC work, the learnable positional structural encodings, one of the works of Dominic. So that work would actually help you to derive universal features, structural and positional features for any homogeneous work. So here, if we need at least two more relations to have some non-degenerative graph of relations. What was the second question? You're muted.
Okay.
Yeah, sorry. I just my internet died for a second. I haven't heard the last words, but thank you anyway.
Okay. Denise, if you want to repeat your second question, you can raise your hand and do that, or you just do that. Otherwise,
Okay. Yeah, my second question was just about weight, adding some weights to the edges
right.
in the edge graph.
That thing doesn't transfer. So we explored that idea. There was actually there was quite some work in that direction, and any sort of weighting that you hard code to some training graph is not transferable. So that simply doesn't work. Well, it actually works, but much worse, and I'll show it in one of the ablation studies. So it's one of the possible things, but it just doesn't work at all.
Okay, thank you.
Yeah, so then the main process, just three steps that you need to that we need to use to apply ultra is so given that the original graph, it's any multi-relation graph, no input, no edge features, we have a query like Michael Jackson and genre something. We want to have a distribution over all nodes that might be possible tails of this triple. And step one is that we build a graph of relations. That thing is actually pretty effective. So for each of those four meta relations, we only need one sparse matrix multiplication. So this is all this relation graph construction is done in linear time with the SPMMs. So no big deal. It's, we can cache it, in fact. And so yeah, that's pretty effective. Then since we know the target relation, we use the MBFnet trick with the labeling trick, but on the graph of relations. So we know the genre is the query relation, so we initialize this genre node in this graph of relation with some vectors. In fact, it's a vector of all ones. It's worth. And all other nodes we initialize with zeros. There are some certain theoretical implications how you initialize this node and with what you initialize, but luckily there was a nice paper by Ismail Ceylan and the Oxford folks on studying those labeling schemes. And in fact, initializing this with the vector of all ones also works. So our very basic initial feature, transferable across everything, is in fact vector of all ones. So then we run the message passing, and we have the final node states of this relational graph would be our edge type features. And here, a cool fact here is that those final features are unique and relative to the starting node. I see a question in the chat. Can we do soft MBF net labeling trick to deal with partially overlapping sets of relation types? I need more visual example.
I mean, if I understand correctly, right now, and I may misunderstand something, but right now you simply learn conditionally on a particular relation type, but still you simply learn those original relation type embeddings from this edge graph, but you do not use actual relation, like original relation type embeddings in any way. You always compute them like again, simply from topology. So there is no way to deal with overlapping edge types, like to propagate this information if I understand correctly. If in one knowledge graph you have like part of the edges that transfer actually to the other knowledge graph, and you want maybe just to take the embeddings as they are, but I guess you can do this blending on the level of the regional graph.
The conceptual answer to that is that relational entities in any sort of graph reasoning are not important. Their relative interactions are important. That's why the whole idea of inductive GNN, so that let's throw away all the identities of entities and relations. We don't need them. What is more important is their interactions. So for node level link prediction, this is the conditional message passing with labeling tricks. Again, you can drop relations there. And here, even if two graphs share 1, 2, 3 edge types, their interactions with other relations will be different. So again, sticking to the identity of those relations is not a good idea. It's far more beneficial to reuse their relative interactions. And there we might actually find similar patterns, how those relations interact in different graphs.
Yeah, it is hard for me to visualize, but it seems that there can be some distribution shifts. Like, for example, in one graph, you have a fraud detection, and a very rare edge is a fraudulent edge. But in another graph, you have a similar distribution of edges, but actually rare edge means like success rate or something like that. And I guess those two edges will be related in your approach.
Well, there will be distribution shifts, and there are still some theoretically unexplored, relatively less explored moments here. So far, I will show in experiments that this scheme works for any multi-relation graph ever. So we have certain assumptions to think that, well, the thing works for any multi-relation graph whatsoever. And there might be other ways to mitigate bigger distributional shifts.
Thank you.
Already. Yeah, so we stopped here on the step 2, that we have our final node states on this relation graph, and those are edge features that we'll be using in GNNs. A cool fact I'd like to highlight here is that those final edge features are based on the genre relation. So if we have a different query, say Michael Jackson collab something, we would initialize collab node here, and the message passing procedure will run and will return different final representations. And this bumps the expressivity so well. This allows us to have much smaller models and to be very competitive and very expressive. Because instead of having one single representation for, say, relation genre or for relation collab, we actually have different set. The whole matrix of relation types is different for any given query relation. And this bumps the expressiveness very well. So here at the output of step 2, we have a unique matrix of edge features. And then we send this matrix of edge features to whatever entity level GNN, which is, it can be another NBFNet, and it can be A*net or some other inductive link predictors. We use this as a labeling trick on the query node. So we put this genre, whatever relation, whatever representation we got from the step 2, we put it on Michael Jackson node, and we initialize all other relation types from our matrix, and we run message passing. So at the end, this is the inductive link predictor, and can be used for any inductive link predictor GNN. So cool features of that approach is that we still do not need any input entity relation features. It's possible to attach them. There are some tricky ways that we have to deal. For instance, different dimensionality of node and edge features. We only have we only have very few learnable parameters. So the 4 fundamental relations that we learn in the metagraph and GNN weights. So the model is pretty small. We can generalize to any graph of any size with any relation vocabulary. So from the graph of a few hundred nodes to huge graphs of millions of nodes. as long as they have several relation types, we can work with them. And yeah, it allows zero-shot inference and fine-tuning on any graph. So as a so think of it as we have found some fancy way of doing tokenization in language models. That when you have any new incoming language or sentence, you can still tokenize them to feed it to a language model, and then you have your learnable vocabulary of embeddings that you have in language models. Now we have a certain invariable tokenization strategy, which is here is done through metagraph and relation graph, and we can tokenize any input graph into that scheme and reuse one same train model. Yeah, so the coolest part, experiments. We run experiments on any existing multi-relation graph in the literature. In fact, we ran out of them. So if you have more somewhere up your sleeve, let us know, because we just exercised all of them. We run experiments, I think, on overall now almost 70 different graphs. And for something that, for some of those that report some state-of-the-art baselines, we combine them here in a table. So here we train one single model on 3 standard graphs in the literature. Those are encyclopedia-style graphs like Freebase, Wikidata, and some WordNet. Those are graphs of different relational distributions. So one single model, we train it on 3 graphs, and we just run zero-shot inference on everything else and see what happens. And in fact, we see here the average column. So you see that the zero-shot performance, zero-shot inference numbers, and those is much better on average, averaged across 40 graphs here, than a bunch of tailored models. So the state of the art here is a model that is trained end-to-end in each of those graphs. So it tailors either to both entities and relations, or at least to relation types. And we see that one single model outperforms by very good margin most of other baselines. And since those graphs are very different in size, from 1,000 nodes to 100,000 nodes, and in terms of number of edges, also from a few thousand edges to millions of edges, we can still run some fine-tuning, and with fine-tuning bumps, well, kind of mitigates the distributional shifts, especially on those very large graphs over here, and it bumps the overall performance even more. A question by Pasquale: do you think that the information captured and transferred by Ultra would also be available in some LLMs? It's a hard question. My gut feeling says no, that in LLMs you need some language representations of those edge types. So you need actually to describe them in language, what those relation types mean. Sometimes you don't have the description, it have to be inventive. Here we are, we take the structural patterns. So think of them more as structural and positional encodings that you can infer from any possible graph. Most of them, well, the most effective of them are based on PPR. And can you get the PPR information from language model? Perhaps you can, or if you shake them really well. But probably just easier if you have a structural model which only needs the graph topology adjacency, maybe easier just to compute as a function of that, and don't use other hammers for this now. So far, I would think that LLMs will be too much of a different hammer for this type of an AI.
But maybe for
Okay.
relation
Please.
extraction, it can be nice.
Mm-hmm.
Like, I mean, like in LLMs, you can also maybe retain on code and kind of solve tasks involving code. So maybe like you don't need to serialize kind of the graph in language. Maybe like as long as you have any symbolic representation for the graph, maybe you're good to go. So like, yeah, that's since like I was reading Ultra, like that was so always that was like in the back of my head, like whether like the same information could be, for example, in some LLM that was also pre-trained or large amounts of code. Maybe it could also have captured those patterns between symbols, and it's able maybe to transfer them to like other tasks. Like,
mm-hmm. Another problem with LLMs would be they're a very small context size. So if we have like 1,000 relation types, and we want to stuff them to LLM to have some sort of an encoding, not many language models would allow you to do so. Of course, there are many of them which allow like context size of like 64,000 or so. Still, you cannot stuff all the make a sort of full batch process of graphs with the lens. You'll have to resort to some subsampling, and that loses expressivity.
Well,
yeah,
if I can
Dominic. There was a lot of questions. Cool. Go ahead, Bruce.
Hey. So one question I had is like with LLMs now you have RAG, retrieval augmentation, so you can kind of carve out the part you need and put it. It's not perfect, but you know, it's something you can manage. But I would be very much interested in knowing whether or not prompting with an LLM versus running your method on a graph, how do they compare and what are the weaknesses and the strength of each? Because you're working a lot with Wikidata, which is Wikipedia style information that exists out there in the form of text, right?
Yeah.
So setting this up as an experiment would be very interesting. And even actually, is there a way of prompting LLMs with these embeddings that you learned, focused on the structure of the graph, and maybe getting better results from the LLM? In the end, I think one of the main purposes of these knowledge graphs is extracting knowledge. Question answering is a natural way of getting knowledge. And I think there is a place where language and these graphs have to meet. And that would be some interesting future direction, I think, to try.
Yeah, I think it's actually so far the most requested feature in the repo. Just folks asked to, can you add some integration with which models here? So we are looking into that.
Thanks.
Thanks, Michael. I think it's very cool work, and especially like the empirical results. I mean, there's a clear gap between like the work that you've done and most of the state-of-the-art baseline, and so I think it's really, really cool. I have a few questions. Like you say that this is equivalent of like pre-training positional encoding, for example, but like for sort of like knowledge graph. So have you tried to visualize like what the embedding look like, or what kind of clustering the model tries to learn? We see that often like in foundation model for like LLMs, where they visualize the relations that are learned, or like structures that are learned. And is there something that you've done there to do this?
Yeah, that's actually a good question. So I would go back here to the slide here. So it's not that easy to visualize embeddings of entities and relations here, simply because they are relative. They are different all the time. So for each of the relation in your graph, you'll have a whole different matrix. So if you want to, the matrix, if you do the say t-SNE or UMAP decomposition for the output of genre, it will be very different from that if you take the decomposition of any other relation. So if you want, so you in that sense, you won't have one image of say t-SNE 2D projection, but you will have many of them, each for the relation type. Then in those you can actually maybe see some simple clustering. Actually, good idea. We haven't done that. And the same for nodes. So we'll have conditional node representation, so pairwise. It means that we don't have that GNN like output, node level GNN output that you can send to some project visualization method, but we have the pairwise relationship all the time here.
Okay.
So it's a little tricky to work with them, to visualize, because they represent pairwise connection. This is not just the identity of a node in this case.
Yeah. And here, when you do zero shot on like the benchmark, like what's exactly the setting? Like my understanding is like to be able to do zero shot, like you need the task to be exactly the same, right? Like what's Yeah. How does your zero shot work?
Yeah, so in each of those tasks, we have an input adjacency matrix with the relation types. And we have node and relation IDs spanning from zeros to whatever final number of nodes and relation types you have. And you have queries in that term, but they have numerical IDs. But basically, they say that some node from this graph and some relation type from that new graph form a query, and then you have to build a distribution over all nodes to rank the nodes. So surely relation one in one of those graphs will be different from a relation one in one of different graphs, and that's why we need some universal tokenization scheme for that. So we understand that the relation one as number one has no meaning. It's the relative representation that makes sense.
Okay, cool. That makes sense. But must have taken like lots of time to really understand how to do that.
Think of that as actually running some structural and positional encodings as a function of adjacency. This approach is a function of adjacency, just a learnable function of adjacency, thanks to this additional metagraph representation.
Okay, cool.
So we practically need only the adjacency.
And one last question. I'm not sure if it's similar to what someone else asked, but here, well, you have the new state of the art everywhere except WordNet. What is going on, and why are you failing at cracking WordNet?
Because WordNet is a weird graph. In fact, it's a tree. It's not a graph. It's again part of my criticism on using this necromancy of graph datasets, which should not be used in the community. So WordNet is a tree, is a binary tree, and the best working models are hyperbolic models because they just best in representing tree structures in some latent space. So it's hyperbolic models will be the best, and so it has only 11 relation types, so the smallest number of them all. It's a very sparse tree-like graph, so it's more of a tree than a graph. So let's just. I would ask the community like, let's forget about the WordNet, but no, reviewers still ask for WordNet. Have to deliver.
Reviewer is always right.
Yes.
Okay.
I say question of Eric. Please hand.
Yeah. Hi, Mike. Great work. Amazing stuff. I wanted actually to ask something related to the previous answer. So, given that you're looking at meta structures like head to tail type of relations and everything, and then initializing any given relation, propagating the message. So, I wanted to ask, like, how much are the meta structures of the derivative graphs from which you pre-trained on? How are the derivative knowledge graphs different in terms of their meta structure on average from the actual thing that you pre-trained on? Because essentially the question stems from you will be capped by how much you know about the main graph if everything you derive from is very similar to it. Essentially, if you're very good on FP15K, and every like variation of it has the very similar meta structure, then you will also transferably be very good at that. Have you looked into something like that?
Yeah, so we want them to be as close as possible, but in fact they are very different. So in the relation graph of WordNet is almost a click. The graph of Freebase, the metagraph of Freebase is more sparse. So they are usually quite dense. I would say half of possible averages, but we have 4 relation types, so that's just divided even by 4. So generally, yeah, there is some distribution shift. They are different. Some of them are clicks and fully connected clicks. Some of them are more sparse, but we still manage to have the same model transferable to absolutely anything. A good part of it is this labeling scheme with all ones. It sort of like softens things up a little and makes them more uniform. Some other schemes didn't work out that well. So for instance, if we use any sort of weighting based on those weighting by node degree or something else pertaining to training graphs, that we lose all the transferring capabilities.
So in in essence, if you were to transfer to a graph that has like like for example, somehow I don't know, bio interaction graph that has no connection with WordNet, FB, and like has a very different, how do you think the method would fare? Would it still be like, because it's in similar subgraph like metastructures? Yeah, that's actually what I wanted to add.
Yeah, there we go. So here we have the same pre-trained model from all those from that huge suite of experiments, and then we try it on some very different graphs. One of them is HitchUNet. This is a biomedical graph called it has to do with biology in graphs. And we beat the supervised SOTA already in a zero-shot mode. Well, it's on par, but if we just fine-tune it for 1,000 triples, then we largely beat it by a very good margin. There is no existing model that would reach those numbers. Then we tried an urban KG. So this is a spatiotemporal graph. So we for now just throw away all the temporal component there and just predict the geographical location. This is a graph of bus stops in Boston, in Chicago, and New York. And they are, again, the zero-shot inference on that graph already gives us state-of-the-art. With fine-tune it a little, it is much better than everything else. We do have more problems in ConceptNet because it's, again, very sparse graph. It has the same number of edges as the number of nodes. So the zero-shot inference there definitely suffers from some distributional shift. But after, again, short fine-tuning, we almost recover state-of-the-art performance, again, for a model which only has 170,000 parameters. And those are state-of-the-art models on this graph are like almost 1 billion parameter models. I think it's not bad result. So generally, there is some distributional shift, but we can quickly recover that after fine-tuning.
That's fair enough. That sounds great.
Yeah.
Thank you.
There is one more question in the chat that I was wondering that in scenarios where we have expressive real entity features, how the labeling trick and Ultra can somehow be trained to leverage those real features. That's a very good question. That's actually, one of the most requested features we see right now is that, is there a chance to imbue that message passing scheme with features? The answer is easy answer. You can use that. You can use the backbone and train a custom model with your own features. That should really be possible. You can just do torch cat with the edge features on this step, or do torch cat with entity features on the entity level step. If we want to have one single pre-trained model that works with any graph with any possible features, that's a tricky work, because we want to have some uniform representation of graphs with any dimensionality of features, and this is tricky. So suppose Cora has 30 input dimension of 3,700, and Sightseer has 1,600. Some graphs might have language model features of 768, and you need a fixed width of a neural net to work. So you cannot send arbitrary features there. So that's still a tricky part. You can extend the model with your own custom features and train a custom model right now. Extending that to arbitrary feature dimension is a non-trivial task. And that, having said that, I would say that we have some work in that direction. Other question: can you get higher order metagraph by extracting multiple times? Sure, yes. This is just one simple example to capture those higher order relations. There might be different schemes to do that. And we think actually that capturing more stuff, more relational interactions will lead to even better transferring capabilities. So far, this is a very basic scheme. It already works pretty well. So it's actually a pretty open question to try out different schemes. And it is likely you will get even better results. No, we exercised all the questions so far. Oh yeah, one more.
Yeah, I actually thought that you already finished if we talk.
No, I still have a bunch of slides.
Okay, then I will ask then. Thank you.
Sure. Cool. Yeah. So that thing we went through. So we Ultra generalizes to other domains pretty well already out of the box, and you can also fine tune it. And another question is there any difference if you do the zero-shot transfer or you train every model from scratch? So this was a very painful experiment. So for each of those 60 graphs, we train a model from scratch, and we compared it with several times actually to have mean and variance. And we compare it with one single pre-trained model. So the result is that one single model is enough. You don't have to train every model from scratch. So we spent quite some compute to assure you that you don't have to waste compute. Some ablations that actually covers some of the questions here. What happens if we drop some parts from the encoder? So if we drop the relation graph, we already see 10% drop in the performance. If we use any sort of non-conditional GNN that uses hard-coded node or edge features in its relation graph, the drop is even harder. So that's so relational graph is important, and relational features are as important as well. Then every time I talk about foundation models and some, I also hear a question: what about scaling? Can you scale it up? The charge of scaling laws is hard on everyone who claiming to have any sort of foundation model. So yeah, what happens? So generally, we observe some positive improvement from scaling data. So far, you have the performance boost in the zero-shot inference case if you increase the number of graphs in the pre-training mix. So not just those 3 graphs on which you train, but you try training on more. In fact, in one of the checkpoints we have now on GitHub, it is trained on all 50 graphs that we got our hands to. And there is some improvement, although it saturates. So it's a question perhaps also with model capacity. Right now, the model is small, so it's less than 200,000 parameters. So it's perhaps we should scale it both number of graphs and number of parameters. So far, plain increase of model size in terms of number of parameters, say internal dimension, didn't work much. So if we just bump it from 64D to 128D, nothing changes. And there might be some optimization tricks we need to explore here. So scaling behavior is still being investigated. Basic evidence says that there are some improvements. We have to unlock them. Yeah, and that would be almost the final slide. That everything now is published. The paper will be at ICLR, so see you there in Vienna. The code is, and the pre-trained checkpoints are already in GitHub and even on Hugging Face spaces. So you can, we even prepare that for Hugging Face. You can run it on Hugging Face inference on any of those 50 graphs that we have in the suite. The checkpoint is small, 2 megabytes. So you don't have to exercise your internet channels trying to download several hundred GBs of Llama. Only 2 megabytes. You can so the checkpoints are on GitHub actually. So just download it from there, and you can run it already on any possible multi-relational graph. And I have one more slide on what's next, but perhaps if there are some questions, I can take them right now. Yeah, go ahead.
Yeah, I just wanted to ask one very basic question for understanding. You have only 4, so while embeddings for relation types are conditional, embeddings for 4 like primary, both tail to head to head relation types, they are the same. Yes. Across all. Okay. And now, first question, have you tried, you said that it is not really important to keep the identity of the edge, but I just think that for people doing groundwork on biomedical ontologies, like you mentioned UniProt, I think they have a problem with both relations and node types that are redundant, and they need to collapse them, like with cross-linking. Do you think this will be have enough precision to do this cross-linking between edges, between different graphs?
Yeah, that's actually that you can infer from this representation really well. So if the output of this step, you have a matrix, and you can just have a cosine similarity, build some similarity matrix out of it, and they are it will show you which relations have exactly the same, very close topological relations in a graph. So which one can you squash in the end to only one row? So this is a nice sparsification mechanism that you can go from one matrix of say 1,000 relations to a matrix of a few hundred, simply because just put a similarity threshold on that. That should be possible.
Yeah, this is really cool. And the last is not really a question. It's just some kind of a rant. People mentioned how you can combine this with LLM. I really think that this can be useful for named entity recognition and especially relation extraction. But of course, you need to think how to do this combination between purely topological relation embedding and some kind of textual grounded. And I think maybe maybe there is a way to somehow like do this in iterative fashion. Like you start with some guess on the topology of your graph and you iterate it. But yeah, it's a bit vague for now. I guess my question is, do you think this can be done somehow with like malleable topology of an underlying graph?
That will be tricky. So far, we expect the topology to be there, and we rely quite a lot on that. Perhaps if you have some topology learning mechanism, like deriving adjacency from a manifold structure of your data, and put it adjacency in the optimization process, it might help. Seems like a future work. Generally, on the musings of using the output somewhere else, it might be a good idea just to use it as a structural featureizer in the same way as, say, random walk structural features I used everywhere in molecular learning. Here, we already see that those structural features are good enough, so you might not need additional node and edge type features to have good performance. Having said that, I would give a shout out to Pasquale's work on refactor GNNs from Europe's 22, where they show that in some inductive tasks, adding textual features to a GNN actually helps. So perhaps it can be a nice extension project just to add textual features per data set and fine tune that, see what happens. There's a good bunch of ways to have such a pre-trained reasoner in LLM reasoning. I would say that. So we have some projects on that.
Yeah, this is especially interesting how this can be used. Because here the query is simply one relation type, but for difficult logical questions on like a Sparkle graph, I guess it's not enough, and you need to use some more complex queries, and then your conditional space of relation types will explode or something else.
So if you're asking this, and I see a raised hand of Eric, so perhaps I would have one more slide here about what's next, and I highlight here that apart from the working for the Church of Scaling laws, and wearing a hat of theoretician, there were a few very low-hanging fruits are extending this to complex query answering, and in fact, I would say we have some first positive results saying that the model works pretty well. Again, on any possible multi-relational graph, we can answer any kind of logical queries. And something else is, in fact, one single pre-trained foundational model for all node level, link level prediction tasks. Even when you have different node features, you have different number of classes. There is still, well, we have a prototype that say that you can have one model that works on core side zero PubMed on any kind of PyG graph possible. One single model of them. So we'll be working on that as well. Yeah, Eric, you had a question.
I was essentially going to ask about complex query answering, and then you went ahead and answered everything I wanted to ask. So because in theory, like I said, this can scale to any like inductive and transductive complex like setting of like conjunctions, disjunctions, and negations. At least it somehow should.
I'll show one slide what we mean here by complex query answering. So this is the final slide of everything, the final backup slide. So by complex query answering, we say now that we, instead of one simple link prediction step, we have several of them organized in a certain pattern or logical query. So if previously we were thinking only about, say, one-step link prediction, now we have them organized actually in some sort of a complex pattern. And each of those arrows is one link prediction step we have to perform. And now we have additional first-order logic operations on top of that. And there is a direct mapping between those queries and some database querying. With the complex query answering, you can not just traverse the graph, but you can infer missing answers. So something that can be achieved if you had predicted missing links beforehand. So that is the complex query answering task.
You made it. You made it through quite some quite a journey of questions. And I agree with Eric that this is amazing stuff. And maybe it's when you speak of a large or huge happening in the space of knowledge graphs, and then mention a neural Bellman-Ford, then maybe this is another happening. Maybe this was the word-to-back moment, neural Bellman-Ford, and this is the GPT moment. Okay, well, maybe let's see. I'm not the knowledge graph experts, but we have the knowledge graph experts here, like Pascal, and they seem to like it as well. And with that, if we have any other questions, let's get into those. Otherwise, Mikhail, what are your last words?
I'll probably reiterate something that we wrote in the blog post. So as a small shameless plug that the whole community came up with the whole review of everything that's happened in GraphML, including Hannes and including Dominic and including many other experts. So have a read. It's a nice reading for the next few days until ICML deadline and even after ICML deadline. It seems I'm a little bit critical of that and saying that it seems that we have solved all the major problems. Like I put that meme for a reason. I think that after a period of GNS, they solved so many tasks that previously were impossible to solve. Now we have them. They work pretty well, and this is now a question of engineering scaling. So I find fewer and fewer interesting problems in the area of knowledge graphs to work on. Let's say that. There are some few low-hanging fruits, yes, but the community moves on. Well, in fact, the community has to move on if they don't want to disappear as Semantic Web did and some other older communities. And so far, we have everything necessary for inductive reasoning. Now you have one single pre-trained foundation model that can do it pretty well on every possible graph whatsoever. And well, you can imbue it with other. You can add numerical features. You can add LLM features. You can add something else. But practically, it is there. You'll only be increasing some numbers, but it practically won't be very new. So that is my existential crisis I wanted to share with you on this nice day before I say another line.
Okay, that's a very big statement and very interesting to me as a non-knowledge graph person.
Pasquale actually understands me because he said like sad but true, because he was in the same background as I had.
Yeah, Denise.
Yeah, just wanted to ask on that.
Sorry. Wrong, Pascal, I guess. Sorry.
Oh, you are muted.
Okay, Denise,
I
please.
guess this is yeah an example of not being able to go through a narrow passage together. Anyway, I just wanted to ask if you really think that this complex logical query answering will be solved soon, because it seems like this is such a fundamental thing in all of science that like it would be a huge breakthrough. Because, for example, like a lot of drug discovery and like target identification work is based basically on this complex logical query answering. You just try to connect a bunch of enriched entities across different modalities. And yeah, I guess maybe one frontier is this combining knowledge graphs and reasoning and different modalities. I don't think that this will be solved like in a in the near year.
I would say if you have language modality, use language models. Why would you come up with additional noisy structure as extracting graph from text if you can just send it to a language model? As
No, but
this is some external medium that you might not need, in fact. So my go-to rule of thumb is that if I have a language modality, I'm a simple man, I would use a language model. If I have a graph modality, I have to come up with something that better leverages graph inductive biases.
the problem is that language modality is harder to ground. Provenance is harder because, like, I suppose there are ways to do this without graphs, but graph seems like such a natural structure where you have for each connection, original connection, you have a source.
Well, provenance is generally something slightly different. Perhaps for some more for regulatory purposes, you need to understand where this comes from. I would say like use RAG, use graphs with a retrieval augmented generation, and you're good to go. I think there are particularly the last 5 to 6 months, I see a revival in that area. Although the original paper was 2019, I think the first. Now folks finally rediscovered vector databases and how you can vectorize some entities for relations from KG and just send it to retrieval meta generation. I think that will be a nice medium for bridging language modality with graph modality. Yeah, I think there was.
I don't think RAG is as perfect as you imagine it to be, but I think there's still some space for kind of making sure that whatever RAG is telling you is actually coming from the context you're feeding it and not from what the language model remembers.
And I also hear a lot of criticism as to, well, still RAG augmented models can hallucinate. With less probability, but they still do. And so far, the issue is less prominent for high degree, very popular entities, but for rare, for long tail entities, and most of the time you have long tail entities in your graph there, you will have hallucinations all the way.
Yeah, RAG also gets expensive because every time you ask a question, the model has to read again everything you have in the context and then produce a result. Versus if I just gave it, embeddings of these graphs, it might be faster, cheaper. I don't know. I'm still optimistic about knowledge graphs. So
I'll be very interested to see if they continue to live. I've been in the area for quite a while, and yeah, I have mixed opinions. I would say that half of my other work is done with the geometric crystal structures. So we do formatival discovery, and I find that area very interesting. So yeah, even though this January was month of graphs, perhaps my next appearance will be actually from the geometry side.
Okay. Then Pascal, do you have any comments with which you want to finish this?
Is that like for me, or like is
Yes,
just
indeed, because it seemed like you wanted to speak up
no,
before.
like no, just like a comment about like, yeah, why going for knowledge graphs? Which is, I mean, maybe like one. Hey, Michael, do you think kind of NLP will be the next semantic web? Maybe I should have asked this off the record. Like, yeah, and everything will be kind of subsumed by, I don't know, new reps and XML.
Let's say that I have a feeling that computational linguistics would still exist in the same way as description logic exists as a university subject. Will it be in the mainstream of AI technologies? No, probably not.
Okay, then Rajit, please do not wait.
I cried a little after that comment, you know.
Hey everyone. Hi, Michael. Thanks for the great talk. I had to miss the earlier part because of some other meeting. So I was looking at the later part of the slides, and if you have already done it, so I'm sorry for that. I'll go through the paper. But I was interested in knowing about the urban knowledge graph. So we work at um, like with the geospatial data sets a lot at NASA, and we have been looking into some kind of graph-based works. So can you please provide some insights about how the training data is prepared for a data set which comes in an image format or satellite images? So how was the data set created so that we can use it for any downstream task? Yeah, this one, the urban KG.
Yeah. Well, most of the details are on the GitHub page. I would say that we generally the graph has a lot of spatial temporal information like geographical coordinates, some temporal aspects about like which bus stops or train stops are used at what time. We dropped that whole information for now. We stripped it off to the basic link prediction task or KG completion task.
So it was a knowledge graph completion task?
In our case, yes. Yeah.
Okay.
Well, actually, the numbers are the same. So the numbers are still comparable. The thing is that in the supervised code, it uses all temporal information with all the timestamps and some other things. We stripped it off and we still have much better result.
Okay. And what does this point mean? Let us know more domain-specific KG. So are you looking for more
Yeah, simply because we exercised all possible graphs. Like we have 40 something graphs here, then we have 20 more graphs for which state of the art doesn't exist. We set it up. So we overall, I think, exercised all possible graphs in the community. So if you have more, just submit a PR and we'll run the experiments, give the number. It will probably be state of the art, unless it's a very weird WordNet-like graph.
Okay, great. Yeah, no, thank you. Thank you so much for the great work.
A few other comments I see in the chat. Oh, do we still have a few minutes?
Sure, absolutely.
Cool. Yeah. Folks asking what's next and talking about knowledge sheets. Actually, knowledge sheets is one of the works in the complex we're answering. I know about that because we wrote a survey. So yeah, query answering seems a low-hanging fruit. We'll try to have it for ICML in a few days. Yeah, something more interesting on this more foundational area is it seems interesting to design a model that will be equally good on any graph with any feature dimension. Surprisingly, there hasn't been much work in that area. So yeah, the simplest example, train a graph on Quora, run inference on Scissor and PubMed. Will it work? And so far there are some evidence that will probably work, but you have to, it is tricky. You have to be inventive. Yeah, and I would say that also in the graph reasoning domain, there are different opinions. During the preparation of the blog post, we had some different mixed opinions on that. So that whether it is dead or not dead, whether we should have whether we should throw a party and celebrate that we have done everything and we should like move on. Some people say no. We actually there are some more stuff on the theoretical and practical aspects of that. So yeah, we'll see what happens in the next few years.
I think we're excited for a good reason.
I wanted to ask a wild question. So there are like traditional those transductive methods that do some kind of equivariant embedding actually, and then there are like equivariant models for 3D that are much more general, I think. So do you think that there is a way to take some of the ideas from modern equivariant geometrical literature and apply it to higher dimensions of knowledge graphs? So do you think this is like pretty useful, pretty useless because most of the things they scale very badly with dimensions?
Well, the original linear embeddings are geometric models. The problem is that they were linear. All those linear, shallow, transy-like or matrix factorization methods. I would say that in industrial settings they still work simply because they're cheap and they're so easy to run. Like in industrial settings, you can compute transy embeddings over your 1 billion node graph every now and then. It will still be cheap at CPU job. Generally, in the higher level, there is actually a known connection between relational graphs and geometry. If you ask around and say, is there any theorem showing that expressiveness of logical expressions of GNNs has anything to do with the inherent geometry or inherent manifold? That is, again, there is nothing on that. We've done some basic scratch over the surface, and surprisingly, there is no direct connection between expressiveness and geometry.
Yeah, I guess this is even from the mathematical standpoint is interesting, because you can also theoretically do this even in a generational setting where you sort of like diffuse your information, and each node, if you're going to sheaves, then each node can be even like approximating some distribution and so on. I guess not for regular nodes, but for like aggregated nodes that represent some subgraphs.
Generally about topology information and sheaves, I would say that might be another generalizable way of getting transferable topological features. In fact, one of the very first approaches which we tried here, instead of here on this part, instead of labeling trig GNNs, we tried cellular complexes from cellular message passing paper from Michael Bronstein's lab and a few other extensions of that work, and it didn't work that well. So that was more of a topology/geometry bias of that model, and in the end, what worked better is labeling trick-like thing, which is more biased in graphs and in graphs and multi-relational models rather than in topology.
Mm-hmm. Yeah, like the last thing, I just think that from this engineering standpoint, maybe it is still interesting because you may combine different approaches on different problems on the same graph, sort of, because you definitely need very different levels of expressivity for various problems and like reasoning tasks. And maybe it makes sense to jump like from one dimensionality to another, depending on that.
Perhaps so, yeah. I would invite actually to invite everyone to play around with the code base. It's pretty neat and small, so it's very extendable. You can add your custom features. You can add other mechanisms. It's fully in PyG, so everything, all the models you have in PyG, they'll probably work here as well. We'll see if we are the ultimate point of graph reasoning.